find the basis of this vector space. Well, maybe I shouldn't say the basis, because you could choose an infinite amount of bases for a vector space. So perhaps it is not so precise to say, the basis. For this specific exercise, and generally, when dealing with different vector spaces in my life, I like to familiarize myself with them first. Just get to know each other. I think this makes sense. So I have this vector space. I make a very interesting observation. These are all the vectors that are inside of the vector space. And each coordinate is being scaled by A, which means I can just take it as a common factor. And then maybe I'll ask myself the question, do I know what type of vector space this is? Do I know anything about its dimension? Well, I can say this now for sure. It's a one-dimensional vector space. And let me also say this very clearly. It involves all scalings of this vector. All scalings of this vector. So this is equal to that. Okay, so we can think of this as, let's say, I'll call this vector x for the sake of illustration. So let's say this is the vector x. I mean, this is of course in three-dimensional space, so I wouldn't be able to draw it anyway. So this is why you should at least not take this too seriously. Anyway, so it looks something like this, okay? And what this A effectively does is it scales my x up, but it also scales it down. I feel like I should have used green for this. You could think of each arrow as a point at which you can just scale the vector and stop. I'll just make all of it in red. And I'll maybe make scalings in, well, not brown, because brown is very close to red. In blue, I think it is nice. So I want you really to think about this as the scaling of the vector x until this specific part or this specific part, so on and so forth. So this is really the idea behind it. I take a vector which is on the line and I apply every single scaling that exists to it. And while this indeed is a basis, so if I choose the basis in this case to be, so the basis is a set of vectors. In this case, it is just a vector of one set of, one element, one vector, which is this vector. But the basis is not unique in the sense that I could choose another vector on this line and scale it. For example, this is x, right? How about I choose vector, and I'll draw it next to it for the sake of illustration, 5x. And then I take this 5x as a basis. So 5x gives me 15, 35, 55. and I look at all scalings of this, and it's still the same thing. Why should this work? And does this work in the first place? Well, yes, it does, because I just take any vector on the line and I apply my scalings in the exact same method. And number two, if you want to make this extremely rigorous, and I'm right now with this equal sign, I'm referring to this part. If I am scaling with all scalings in R, then it's fine. I can just multiply this by any number, really. Here's why. The answer to this seemingly unintuitive result is the fact that if I take R and I multiply it by 5, I'll still get R. Now when I say multiply 5 by R, I mean you take 5 times x for x in R. This will always give you a number in R. What I really want to say is we have all the scalings in the world. So it doesn't matter if I take this one, or if I take a multiple of 5 from it, or if I take a multiple of 50 or 27.431. As long as my field is here, I can scale it up, I can scale it down. I have all the numbers in the world. And it doesn't matter if I choose a bigger vector, because I can always bring it down as small as I can, and I can always bring it up as big as I can. And effectively, what I'm saying here is that if you take all the vectors, all the numbers in R, and you multiply them by 5, you'll get all the numbers in R back, and you won't be missing a single number. Yes, it's weird because R is an infinite set, but think about this for a moment. Choose a number in R, multiply it by 5. The result will always be in R. This is something I can guarantee to you. You can get me one example in which this fails, I will be I'll be very surprised. So this is kind of the idea behind why this works. And it's not just 5. It's not just 5. It's really, any constant. Any constant. Because in the end, this constant is also in R. And R is a field. It's closed. You multiply 2 elements in R. You get an element in R. I think now it's a good time to stop, because I feel like if I say more things, I'll make things even more complicated. But perhaps to conclude, all I'm saying is that yes, this is the vector x, the red one, but if I take the green one, which is 5x, and why did I do this? I take the vector 5x and I apply all the possible scalings. So let's say I apply them like this. I can scale it up. Or down. And in this way, I can reach any point on the line in the exact same way. It's just that the scalings will be different. And that's really all the difference that you need to make note of, but nothing else. Fundamentally, if you choose any vector on this line, any point on this line, and you keep scaling it with all the scalings in R, then you will always get your whole line back. And this is why if you choose any vector on this line, and this vector space, slash line, you will always have a working basis for yourself. And this is very good in the case that we're looking for a basis. And this is the case here with this problem. So perhaps it's a good time to stop.